Welcome to an optimization example. So in this example, you are hoping to build a fence around a rectangular region with an additional fence through the middle to break the region into two lots. So I have this drawn below. You have materials for 1,000 feet of fencing, and what is the maximum combined area for the two lots? And then what are the dimensions of the optimal rectangular region? So when we start this problem, we have a diagram. We can kind of understand what's going on from the diagram. Our goal is to maximize the area. And then the extra information we have for our limitations would be that the total fencing is 1,000 feet. So first thing first is, in order to find the area of the space, we'll need to do sort of a length times width, like for a rectangle. So you have two options here. You can either do the dimensions of the individual lots, or you can do the dimensions of the entire rectangle. I'm going to do the dimensions of the individual lots. So actually, yeah, we'll do actually the dimensions of the whole one, because I didn't technically specify these two lots are the same size. So we'll do the entire length and then width. And so first we're going to have an equation for what we're trying to optimize. So we want an equation for area, and this is what we're trying to optimize. And so we have area. Oh, I didn't actually label width. There we go. Area is simply equal to length times width. So now what we need is we need an equation relating length and width, and this is usually going to use whatever other information you were given in the problem. So now we're going to write an equation relating length and width. And again, this will use whatever other information we were given in the problem. So we know here that the total fencing should be equal to, we have the entire length from the bottom, entire length from the top, and then 3 of those widths, since there's a line through the middle. So if I went through and labeled these, we have another L up top, and then we have 2 more W's. Right? So total fencing, we have 2 lengths and 3 widths. And then we also know that that total fencing is 1,000 feet. So we have 1,000 feet is equal to 2L plus 3W. And now we're going to rewrite both variables in terms, like, we should rewrite one of the variables in terms of the other. So we're going to rewrite L in terms of W. it's up to you which one you want to do. So we have 1,000 is equal to 2L plus 3W. So if we subtract 3W from both sides, we have negative 3W plus 1,000 is equal to 2 times L. And then if we divide through by 2, we get negative 1.5W plus 500 is equal to L. So again, that came from just dividing both sides by 2. And before that, we just subtracted 3W from both sides. So now we're going to go back to the optimization problem. Or to the optimization equation. And rewrite the equation in terms of W. So once again, we had area was equal to length times width. And we just found length was equal to negative 1.5 W plus 500. So we have area is equal to negative 1.5 W plus 500 times W, or area is equal to negative 1.5 W squared plus 500 W. Now, in order to optimize, we need to know our limitations, right? Now this is quadratic, so it won't turn back around. The maximum is just going to be the relative max because it's concave down. But sometimes we have functions that zigzag around, and so it's important to know our endpoints. So determine the limitations. So we know that length and width are both non-negative. So that length and width are both greater than or equal to 0. And we know length is negative 1.5 W plus 500. Well, we know that's greater than or equal to 0. So negative 1.5 W is greater than or equal to negative 500. And we wind up getting then that W is greater than or equal to negative 500 divided by negative 1.5. That winds up being, dividing by a negative, that's going to swap to be W is less than or equal to, and we wind up getting 1,000 thirds or 333.3 repeating. And now we're going to go ahead and optimize. So we have area was equal to negative 1.5 W squared plus 500 W. We know our endpoints are W equals 0 and 1,000 thirds or 333 repeating. We can find our critical values. So the derivative of A with respect to W is going to be negative 3W plus 500. I'm going to find where this is 0 or undefined. It's a polynomial, it's never undefined. But we do have limitations on where it makes sense to study W, right? It's equal to 0. Negative 3W is equal to negative 500, or W is equal to 500 thirds, which is what, 166.6 repeating. So now we can go ahead and just check at each of those values. So we're going to evaluate A at each specified value. You could also do curve sketching in increasing, decreasing analysis. But again, if the function squiggles more than just a parabola, you will likely want to just do the endpoints and critical values checks. So we have for W, we're going to check at 0. Then 500 thirds, or 166.6 repeating, and then at 1,000 thirds. And then we want to find A, which A is equal to negative 1.5 W squared plus 500 W. So if we plug in 0, that's very clear that A is equal to 0. If we plug in 500 thirds, we need to do a little evaluation here. So if I plug that into my calculator, negative 1.5 times 500 thirds squared plus 500 times 500 thirds, I wind up with area is equal to 41,666.6 repeating. And then if we plug in 1,000 thirds instead, we have negative 1.5 times 1,000 thirds squared plus 500 times 1,000 thirds. We should wind up getting 0, right? Because 1,000 thirds for W wind up being our length was equal to 0. And we do indeed wind up getting area equal 0. So of all of these, this is where we get our maximum area. And the maximum area is 41,666.6 repeating square feet. We're talking about feet for our foot fencing. And the dimensions where this occurs, we had that W is equal to 500 thirds, or 166.6 repeating feet. And then L, we had a formula for. L was equal to negative 1.5 W plus 500. So L is negative 1.5 W plus 500, or negative 1.5 times 500 thirds plus 500, and we wind up getting 250 feet. So the dimensions of the large rectangle are 250 feet by 166.6 repeating feet. So this is optimization. There's quite a few layers to these problems. The more you do them, the more familiar they will get. So for this week, we're just kind of touching optimization, getting started with it. You have a few homework problems where you're practicing optimization. And next week, we will do more practice with optimization.